Here we're trying to figure out if we draw an altitude to the base of a triangle, what happens? Do we form three similar triangles always, sometimes, or never? Well, in the case of a right triangle, right, if I draw this as a right triangle, so pretend this is a perfectly drawn, right triangle. Let me start that over. That's not a very good right triangle. Maybe that's a little bit better. Okay. All right. So here's our right triangle, right? Here's the right angle. And in this case, we're drawing an altitude. Now, an altitude is just a line that we draw from the vertex of one side, so the corner. So let's name these, right? This corner right here will be A, this will be B, and this will be C. So the altitude, let's drop it from B down to the other side, and it needs to be perpendicular. So here we have a right angle here, and on the other side as well. So this is D. So in this case, what we've referred to the mean proportional. Now, if you've heard of the product of the means equals the product of the extremes, that's referring to the situation. Let's say we have, I don't know, 2 over 4 equals 3 over 6. Well, if we multiply 2 and 4, 2 and 6, excuse me, right, that's 12. And 2 and 6 represent the extremes. And here, 4 and 3 represent the means, and 4 times 3 is also 12. Why is it called means and extremes? Well, 2 to 4, the first ratio, if we write it as 2 to 4 equals 3 to 6, right? The numbers 3 and 4 are referred to as the means because they're in the middle. They have a mean, an average. And the outside numbers are extremes because they're outside. So the product of the means equals the product of the extremes. And I'm telling you all of this because in this case right here, with the right triangles, we do get three similar triangles. This is a special case. So triangle ABD, right? So that's this triangle right here. ABD will be similar to, well, let me write it like this, sorry. Similar to triangle, let's get another triangle in there. BDC, this triangle right here, BDC, and I'll make that green. And that will be similar to the large triangle here, ABC. So in this case, we will get these three triangles that are similar to each other. But why means and extremes? Well, this whole idea with the right triangles and dropping the altitude ends up leading to these two useful theorems. So in the first case here, and these are a little bit word heavy, but I think they're worth talking about and showing in a brief example. So here we have the altitude of the hypotenuse of a right triangle. So that means, again, you drop the same altitude. So we'll call A, B, and C. We drop the altitude down here. It's, let's say, point D. There's our right angle. The altitude of the hypotenuse of a right triangle is the mean proportional between the segments into which it divides the hypotenuse. All that means is that the ratio of AD, right, to BD, so AD to BD, so leg to leg, right, equals the ratio of BD, right, to DC. You can see that in this right triangle, that was just the ratio of the two legs of this small right triangle, ABD, equals the ratio of these small legs, larger but small, large leg ratio in BDC. We're just saying the ratios of the legs are equal. And it's mean proportional again because the two means are B and D, right? The two middle terms in the ratio, and they're equal. So that's one ratio that's going to be really useful. And you're often given numbers here. So like, let's say this is 3 and this is 4, right? So if you know AD to BD, so it's 3 to 4, and then equals 4 to what? What would DC be equal to? Well, you're going to solve for DC like you solve for X. Multiply DC by 3, we get 3DC equals 16, and DC would equal 16 over 3. So that means DC, this side right here, would be equal to 16 over 3. So you can use this ratio to find that side length. And the last one's very similar. Each leg of a right triangle is the mean proportional between the hypotenuse and the projection of the leg on the hypotenuse. So here's another description of what's happening in this special scenario. So we draw a right triangle again to understand this, right? And once again label our points A, B, and C. So here's A, here's B, and here is C. And as a right angle, we drop the altitude down. Okay, it's at point D, forms a right angle. So what does that mean? Well, it depends how we order this, right? But here, let's say we look at this large hypotenuse AC, and we say the ratio of AC to the leg AB, right? That ratio is the same as AB. So here, AC is a hypotenuse, right, of the largest triangle to a leg AB. AB is a leg of the largest triangle, but then AB is also the hypotenuse, right? So this is hypotenuse. And for this triangle over here, so AB to, again, AD. That's a leg. So it's hypotenuse to leg is the same as the ratio over here, the hypotenuse to the leg. And, we can look at it in other ways. Let's say we have AC to the other leg, here, BC. So here we could write AC, a hypotenuse, over BC, another leg. What would that be the same as? Well, BC is the hypotenuse for this right triangle over here. So BC, right, the ratio of BC equals the ratio of BC to what? Well, it's hard to keep track here the way I'm drawing it, sorry, but AC to BC, BC is the longer leg here, so BC, the hypotenuse, would be the same as the ratio to CD, right? We're just playing with these, right, mean proportionals here. That the legs are the mean proportional because they form both leg and hypotenuse in two triangles. So what's all this about? Well, go back to our original question. It's asking, when does the altitude divide a triangle to three triangles, similar triangles? Well, when you have a right triangle. So the answer is sometimes. But from that comes this whole other exploration about similarity and these theorems about the ratios of the sides in the similar triangles. All right, thanks.